Hello and welcome back. Today I want to continue looking at the transmission line balance we discussed last time, the half wavelength one and the 1 3/4 wavelength implementation, by building and performing some experiments. So even though these two types are widely used, there might be some interesting observations to be made. So if you're curious, then keep watching. The two types of Balun highlighted are the most common implementations you will find when you need a 1-to-1 or 1-to-4 Balun. So other than seeing that these actually work, what I want to check out today is the impact of the transmission line itself and the operating mode. The simulation predicted that one of these is a current Balun and the other a voltage Balun. Now, even though transmission line structures can be used at any frequency, these are usually considered only when working above 100 MHz. The main reason being that otherwise the wavelengths are so long that the transmission lines used would be too bulky and too lossy compared to other options, like transformers. Regardless, to make today's experiments easy to measure, I will be using some relatively large pieces of coax that allow the creation of baluns that work below 20 MHz. So at these frequencies, the exact measurement and signal generation are not all that difficult. So first thing to play around with is the half wavelength 1-to-4 Balun, and I built this with about 10 meters of 75 ohm cable. So the impedance of this cable should not really matter, everything else is 50 ohm cable, just this is 75, and for this I connected one side to the signal generator and the other to a 200 ohm load, and I'm measuring this using 3 channels of the oscilloscope. So what we will be seeing are the 2 branches of the termination as well as the ground current. So let's now look at the various measurements in a bit more detail. So after playing around with the generator a bit, I found the exact half wavelength frequency at 12.4 MHz. Here we can observe the 2 signals, so the blue and the yellow one, being 180 degrees phase shifted. And well, there's a very small ground current, so the one in pink, so the load is not perfectly balanced. After all, I'm not using any special high precision resistors. But anyway, at this particular frequency, the Balun is providing a differential signal into our load. We can also play around with the generator a bit and highlight the delay behavior of our transmission line section. So at double our initial frequency, at 24.8 MHz, the transmission line has a full wavelength length. So the signal arriving at the other end of our termination is in phase with our initial signal. And this is exactly what we see in our measurement. Both branches are in phase, and all of the current is going to ground. Next, to confirm the input side impedance of our Balun, I measured the signal that would arrive in the Balun when there is no load, and then when there's a 50 ohm termination. So with an open line, we are measuring about 2.02 volts RMS, and into a more or less ideal 50 ohm termination, we have half this value, so 980 millivolts. And next, when we reconnect our load, the voltage present at the input is a close enough 972 millivolts. So even though the transmission line used for the Balun is 75 ohms and the termination is 200, the entire structure behaves like a 50 ohm load. So the impedance transformation is working as expected. Finally, it's time to observe the behavior when an unbalanced load is provided. So for this, I added an extra 100 ohm resistor in parallel with the initial resistors, so that we can get 50 ohms on one side or 50 ohms on the other side. So I did both experiments just to see how well balanced the entire system is. And if we plot out these results, our first observation can be that the voltages do stay the same. So regardless of where the imbalance is and the fact that there is an imbalance, the voltages on the 2 branches of our Balun are exactly the same. So we can confirm that the behavior of this structure is that of a voltage Balun. The voltage stays balanced regardless of the load. The other thing that we can observe is now that we have a very clear ground current. So this is happening because of our imbalance. And we are getting the ground current in phase with the signal side with the smaller resistance. So the side in which the current is larger. So the half-wavelength balun is behaving as expected from the simulation. No special surprises. It's not impacted by the half-wavelength transmission line's impedance, and it does behave like a voltage balun. Now it's time for the other balun. And let's just say that things don't go as easily there. So this time we have more or less the same setup. The load was changed to have 50 ohms. We're using the same signal generator and oscilloscope to make the measurements. It's just that the balun is now made from two large pieces of cable. So I had this older 8.3 meter section, and I have this extra 25 meter section. So both of these are 50 ohm cables, both of them are from the same manufacturer and the same order code. It's just that one is 3 times longer than the other. So let's now turn on the experiment and proceed to look at some measurements. And, well, from the very first measurement, we are running into some issues. So at around 5.77 MHz, the two signals arriving at the two ends of our load are 180 degrees phase shifted, but they are clearly of different amplitudes. Now, I'll be going into some investigations later on regarding this, but for now, let's continue with the other measurements as well. So next, if we double the test signal frequency, I went up to 11.54, we are getting the same effect as before. Both signals arrive at our load in phase, and all of the current that is injected into the load goes to ground, so we have a very clear ground current. So the length of the line is giving us the expected phase delay, but again we can see that our yellow signal is slightly larger than the blue signal. If we continue with the impedance measurement, I redone the reference measurements at the new test frequency. So again we get about 2.02 volts into an open load and 0.995 into the 50 ohm termination. And if we measure the complete balun structure with the 50 ohm load, we get a very close 0.99 volts RMS. So from the input side at least, the structure is behaving as expected. It's showing 50 ohms. So it's not clear that there's anything wrong on the load side. Finally, if we check the operating mode of the balun using an unmatched load, so I added an extra resistance in parallel with one side and the other to get about 16.7 ohms. When we look at the actual measurements, on one of our measurements we get a very nice match, whereas on the other we have a very large imbalance, but we can also observe that our ground current stays more or less the same with the two unbalanced loads, as well as with the balanced load. So this does confirm that our structure does have a current balun behavior. Regardless of the imbalance of our load, the current that goes into one end comes out the other, and the voltages are load dependent. But for whatever reason, with the practical setup, there is a current imbalance. This was quite a strange outcome. The experiment was supposed to work. But where did the unbalance come from? I had a few suppositions. The small signal was on the long wire, so maybe it's an issue of cable loss. We are talking about a 25 meter long structure after all. Well, to investigate, one avenue was to go back to the circuit simulator again. So I created a transient simulation to better reproduce our experiment. And here there are a few things to change. So starting off from a reference circuit in which we have two line sections, one that is 3 times longer than the other, and we have various things to compare it to. So our practical setup is not perfect, of course. So the first thing that might be an issue is the exact length of cable. So getting the lengths perfectly 1 to 3 is not always possible. So the first simulation involves having one of the cables slightly longer than we're supposed to have it. And well, if we look at the two signals, as long as we readjust the frequency, they're again both the same amplitude and with the correct phase offset. So the imbalance in the length will just change the exact operating frequency. Another issue that you might have is the exact load that you're using. So in practice, I'm using 51 ohm resistors, not 50, so the system isn't perfectly matched, and to see the effect of a improper load, I created this other test circuit in which the load is 52 ohms. So if we look at the amplitude here, well, again we see a nice and balanced signal. So even if you don't have the right load value, as long as it's balanced, the result will be as expected. Now, the last thing to look at is the cable's exact impedance. Now, according to the datasheet of the 50 ohm cable that I'm using, the characteristic impedance is 50 ohms plus minus 2. So a small mismatch, say half an ohm, should be perfectly realistic, especially considering that the two pieces of cable that I'm using are coming from different production lots. So if we look at the response of this circuit, in which the cable impedance is different, well, we start to see a behavior similar to what we are getting. So at least in the simulation, when the line impedances of the two pieces are not exactly the same, we are getting a very clear imbalance in the two signals. So is this the problem that we're having? To verify what was going on, I took the long cable and cut it into two sections, a 6.25 meter section and an 18.75 meter section. So now, both of these are made from the exact same cable. Now, based on the new lengths, I had to readjust the frequency, and this time at 7.79 MHz, where our two signals are 180 degrees phase shifted, we still have the same issue. But this time it's slightly better. So the difference in between the two amplitudes is slightly smaller. So even though it's the same cable, the signal on the shorter length, so the blue one this time, is larger than the signal on the longer piece of cable. Maybe it is an issue of losses after all. Anyway, one final thing that I tried was to change the load impedance. So the idea was that if the load impedance is, say, 200 ohms, the current traveling through the transmission line will be smaller, so any resistive losses will also decrease. Now, since the input to output impedance ratio is dependent on the line's impedance, and my line is 50 ohms, you can still get a perfect match to the final 200 ohms if the input side impedance is 12.5 ohms. So the Balun, under these impedance conditions, because of the impedance transformation of the quarter wavelength, will be able to match everything up. So as not to complicate things and be able to connect this thing to the 50 ohm output of the signal generator, I added an extra 37.5 ohm series resistance so that everything is now nice and matched. Now, before running the test, we can look into the simulator and see that with this sort of circuitry, the expected voltages that we should get on our 200 ohm termination are exactly the same that we should be getting into 50 ohms with the initial setup. So regardless of which setup is being measured, we should be seeing the exact same voltages. And well, in practice, if we put side by side the two measurement results, so our initial one with the 50 ohm termination and then the new one with 200 ohms with the extra 37 ohms series, well, we have the same imbalance. It's just that since the currents are slightly smaller in our second circuit, the losses are also smaller. So rather than getting 500 and 400 millivolts, we are getting 500 and almost 50 and 430 millivolts. So we still keep our imbalance. So if this is a problem of losses, it's not a problem of resistive loss, it's a problem of transmission line dielectric loss. And to finish the investigation, I made one final set of simulations. So LTSpice also contains the option for modeling lossy transmission lines. With this option, you can model a transmission line by giving it a specific length and then characterizing the parameters of the unit of length. So you have various parameters that can be defined. In my case, I just defined the length in meters and then try to calculate the specific inductance and capacitance per unit of length and the DC resistance from the datasheet. So I took my two pieces of transmission line with the 6.25 meter length and 18.75 meter length. And to make the comparison fair, I also created a second simulation in which I just reduced the DC resistance, so kept the same inductance and capacitance, same length, just a very small resistance. So if we perform an AC simulation on this circuit, starting off with the ideal lines, well, at almost 8 MHz, just like in our practical circuit, we see that the two signals arriving at our load should be identical. And if we move to our more realistic cable, the one with the included losses, on the shorter end, we get more or less the same signal as with the ideal cable, but on the long piece, we start getting a noticeable difference. So if we just plot out the real cables, we see that there is a very clear difference, even though the value isn't all that large. So we have 1 decibel per division, so this difference is about 0.3 decibels. Now, another interesting thing that we can see from the simulation is that at double this frequency, so when the two signals should be in phase, their amplitudes are almost the same. So to some extent at least, this matches up very nicely with our measurements, where at the quarter wavelength frequency we were seeing a relatively large difference, but a much smaller difference was observed at double that frequency. Now, last thing to mention is that even though the difference that we are simulating is not the same difference that we see in real life, this is caused because I'm only simulating the DC resistance. I'm not simulating the AC resistance. So every cable will have a certain attenuation based on frequency, which will explain our larger difference observed in real life. Well, I guess one reason for not making baluns from tens of meters of cable will be the various losses that appear, as well as the inconsistencies of the cable's impedance. Anyway, this just goes to show that when you're building this sort of 1 3/4 wavelength balun, the 2 bits of transmission line need to be as identical and as lossless as possible. A problem that does not really appear with the half wavelength balun. Or at least it was not obvious during my experiments. But anyway, I had quite a lot of fun with these experiments and hope you got some useful information out of this. And as always, leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my videos, and see you next time. Bye bye.